All right, today we are going to talk about work. So this is something that is going to add to our energy bar charts and kind of changes how we examine our systems and how energy gets transferred between objects. So first up, let's just take a look at this situation here. We have a spring pushing a car from rest. So our spring is compressed at the start, the car isn't moving, and then at the end, the car is moving. But notice this time, we're saying only the car is the system. In the past, we have always said that, like for this example, we would say the car and the spring are the system, but now we're going to say just the car is the system. So let's take a look at the LOL diagram for just the car. If we do this, we see the car is moving at the end, so it has kinetic energy, but at the beginning, it's not moving, it's not up in the air. The car doesn't have the spring energy, the spring has the spring energy, so that doesn't get included on this L. Again, this is just because our car is the system and we're not including the spring. So we need to find some way on this LOL diagram to account for that spring energy, because we can see the car here, it got its kinetic energy, but this doesn't obey the first law of thermodynamics. This is just showing us, oh, all of a sudden this car just magically got some kinetic energy, so we need to account for the spring energy. The way we do that is through work. So, again, like I just explained, we're missing, what's the deal with that energy? We're not obeying the first law of thermodynamics. So the way we represent that is we draw an arrow and we show, so see how we have 1, 2, 3, 4 blocks of energy at the end here? We just draw an arrow with 4 divisions in it, so 1, 2, 3, 4 blocks of energy, and then we write the spring transferred energy to the car. So that's why we have been writing the system in this O. This lets us show when energy enters our system or leaves our system. We'll see an example of that later on. So the way we phrase this, we say the spring did work on the car. And then our energy equation to represent work, we have no energy at the start, so we say 0, and then we add work, we add energy to the car, and then at the end we have kinetic energy. So 0 plus work equals EK. We're always going to put work on the left-hand side of our equation. So remember that the first law of thermodynamics just says that in a system, the total amount of energy remains constant and energy is neither created nor destroyed. So we kind of glossed over that system so far this unit, but now we're going to be looking more at what's in our system, what's outside of our system, what happens when energy transfers in from outside. If the energy is entering or leaving the system, like we said before, we now define that as work. So that's just energy that enters or leaves our system. If work is involved, we want to put an arrow drawn going into or out of that O, the system, and we want to label where is the energy coming from or where is it going to. Then, for our energy equation, we always put work on the left-hand side, so we either add it or subtract it from our initial energies on the left. If we take a look at this second example, this one isn't in your notes, this is just so you can see what it looks like. This was the situation, so just so you can see everything again, we have our car, so no energy at the start because just our car is the system. The spring does work on the car, so the spring adds energy to the car. And then right here, all kinetic energy at the end because the car is moving. So this is an example of where we have energy coming in from outside of our system. Energy equation, once again for that one, 0 plus work equals EK. Now this one's in your notes, so we're going to try and fill this one out. So we say a moving car rolls to a stop, and we are going to apply friction. So we can see at the start here the car is moving, and at the end the car is not moving. And it says only the car is the system. So we're going to try and draw an LOL diagram for this one. So if just the car is the system, that's what we put in the O. At the beginning the car is moving, so we need to have some kinetic energy. And then at the end the car is not moving. So we have 0 energy at the end. What we would have done last unit is we would have said EDIS, or not last unit, last worksheet, we would have said EDIS. If you remember problem number 6 from worksheet 3, that was where the soccer ball rolled to a stop. And then we said the soccer ball and the ground were the system, and we had basically kinetic energy equals EDIS. It's going to be a little bit different now because we don't have the ground as part of our system. So what we need to do is say all of that kinetic energy from the car, it left the car and went into the ground. So we just say the car, in this case, did work on the ground, or the car transferred its energy to the ground. So that's what the LOL diagram would look like. You can copy this down in your notes, pause the video if you need to. Our energy equation for this one, we have EK. This time we are losing energy, so we say minus work equals 0 because we have no energy at the end. Here's the next example. We have a spring launching a car uphill and no friction in this one. So we're going to say just the car is the system. So again, look at the start. We have the spring coiled up. The car's not moving. It's at the bottom of the hill. Then at the end, the car is moving and it's higher up the hill. So if just the car is the system, let's draw our LOL diagram. If you're feeling confident, pause the video here and try and draw it for yourself before you check. But we'll go on. So the car is our system, just the car. So that goes in the O. At the beginning, the car's at the bottom of the hill and it's not moving. Remember, the car doesn't have the spring energy. The spring has the spring energy. So no energy at the start. At the end, now the car is up in the air and it is moving. So we have some EK and some EG because once again, moving, so we have kinetic energy. Up higher up the hill, so we have some gravitational energy. So we need to account for where it got that energy from because again, we're not following the first law of thermodynamics right now. So we need to say the spring did work on the car. So notice one more time here, 1, 2, 3, 4 blocks going into the car show these divisions. So you obey the first law of thermodynamics. Don't just draw a random arrow. We have 1, 2, 3, 4 blocks of energy going in, and we have 1, 2, 3, 4 blocks of energy total at the end. If we were to write an energy equation for this one, it is just 0 plus work equals kinetic energy and gravitational energy. This time, we are going to look at it, but the car comes to a stop. So same starting, we have the spring coiled up, the car's not moving at the bottom of the hill. This time, the car is all the way at the top of the hill. It went so high that it stopped. So we are going to update our LOL diagram. Again, pause the video here, try and draw it for yourself. We want to put the car only as our system. And then we say at the beginning, remember the car not moving, so no kinetic energy, bottom of the hill, so no gravitational energy. The car doesn't have the spring energy, the spring has the spring energy, and it's not part of our system, so no spring energy here at the start, and no chemical energy. At the end, it is at the top of the hill, so it's just all EG, because it has come to a stop. We need to account for where that energy came from. How did it get pushed up to the top of the hill? The spring did it, so we say the spring did work on the car. Once again, notice 1, 2, 3, 4 blocks of energy, 1, 2, 3, 4 blocks of energy at the end. So this is obeying the first law of thermodynamics. Energy equation, 0 plus work equals EG. This last example, we are going to look at the same situation, but now using the spring as the system. So we're going to shift our perspective a little bit. We're not going to look at the car, we're just going to look at the spring. So think of this from the spring's perspective. At the beginning, the spring is coiled. At the end, the spring is uncoiled. So here is the LOL diagram for that one. We have spring energy at the start. Then at the end, it has transferred its energy to the car. Our energy equation for this one, we have spring energy at the start. Notice this time it is minus work because we have energy leaving our system. And then at the end, we have no energy left, so it's just 0 because we have transferred our energy away to the car. This next one doesn't go in your notes, but it is just a good reminder. So just kind of picture this one. We have a diver running off a cliff. So the start is the diver running on top of the cliff, and then the end is just before they hit the water. So think about what this would look like on an LOL diagram. If you want, you can pause the video and just sketch it in your notes. If we were to draw this one, it would look like, first we got to put the diver in as our system. At the beginning, they're running on top of the cliff, so they have some EK and some EG. Amounts don't matter here, just some of each. And then at the end, they're about to hit the water, so we say they're like a millimeter off the water, so we can round their EG down to 0, and it's just all kinetic energy. Notice this one doesn't have work in it. That's just a reminder that we did do stuff earlier this week. Not every situation is going to have work. So if all of the energy stays within the system, we just keep doing what we have been doing. But if energy enters or leaves our system, which doesn't happen here, then we need to include that work arrow. Our energy equation for this one is just EK plus EG equals EK. Once again, no work here because all of our energy is contained within our system.